Okay, 4.1 today, we're going to talk about the exponential properties. No, done. There's one that works. Okay, what do I need you to be today? I need you to be forgiving. Forgiving of logs. Seriously, all your dreams come true in logarithms. All your dreams come true. They do. Yes, but Denise, what am I asking you to be today? Forgiving, right. Which means you got to take out your notes, you got to take notes, you got to do all those things that good students do. Let's talk about goal for today. Number one.
You know who else's class I took notes with? Yes.
She had a baby. Baby Andy, she had a girl. I'll show you the picture at the end of the period if you remind me. Yesterday afternoon.
Yeah. Yeah, Mr. Bravo and Alex.
Yeah.
You're watching a movie.
Shh, hand, let's go. I want this to be less than 20 minutes. Understand exponents and their growth rate. This, shh, guys, stop talking. There should be the natural log of 1 talking right now. That's equal to 0. Okay, this is a big thing for calculus because you have to understand which one of these functions goes faster and which ones go slower. And number 2, you need to understand the inverse properties. You just understand the inverse properties of exponents and logs. Okay, what's an exponential? Sloppy definition is multiplication on steroids. Guys, stop talking. There should be no talking. Exponents on steroids. So in other words, f of x is equal to like 3 to the x power. Or we're just simply asking a question, how many times are we multiplying 3 by itself? Yeah, x times. Okay, so here's my question to you. We're going to compare this to this. Oh, g of x, can't use f twice.
Multiplication on steroids.
Yeah. Hence why I said it out loud. Okay, let's compare to switching the 3 and the x. Okay, so here's what I'd like you to do. X, f of x. Okay, real quick, which one do you think grows faster? Cubing some number or 3 multiplied by itself that many times? Okay, it's just a preliminary vote. How many say, man, 3 to the power, that's going to grow faster? How many say cubing, it's faster? How many aren't going to vote no matter what I say? Too scared of logarithm. Okay, let's plug in some numbers. 1, 2, 10, 100. 1, 2, 10, 100. Take out your calculator, plug those in. 1, 2, 10, 100.
1 times 1 is 1.
Plug that into F, plug that into G, which one grows faster? Plug that into G, which one grows faster?
Yes. It's out of 51, but the IKEA grades out of 50.
Oh, we'll put it in the grade book out of 50. I forgot I did that. Slackers, they just want to make their lives easier. Okay, some dog questions. The first power is equal to what? 3. Easy. 3 to the second power is equal to what? 3 to the 10th power. Volunteer to read it. 3 to the
59049.
Okay, so look how fast this went up. Right, so when I start talking, you got to stop. Don't make this annoying for me. I won't make this annoying for you. At 1, you're 3. At 2, you're at 9. But you just go to 10, and you're above 50,000. Slow. Yeah,
Whoa.
it's multiplication on steroids. Most people think the cubic grows faster. No, multiplying a number by itself 10 times is going to go way quicker than multiplying that number to the 10th, or that 10 to the third power. 100 volunteer?
It's 5.15 times 10 to the 47.
5.15 times 10 to the what?
47.
Okay, now real quick, that means there are how many zeros behind this? 47 numbers behind this. Oh, 45 zeros, correct. 45 zeros, 47 numbers behind that. Is that a big number or a small number? Yeah, you want that. You want that in your bank account. Let's go over here. 1 to the third power is what? Power is what? 1. 2 to the third power is 8. So notice this is already past this. This is already past this. 10 cubed is equal to what? Is it even close? No. And notice, is 3 even that big of a number? No, if you plugged in 4 here or 10 here, this is going to go up even faster. This is what you want your bank account doing. You want exponential growth. You don't want cubic growth. 100 is 100 cubes equal to what? 1 million. How many zeros are behind the 1? How many zeros are behind this? 40. Yeah, a lot. So which one grows faster? The exponential grows very quickly. The exponential goes very, very quickly. It's not even close at 10. It's not even in the same like universe at 100. You go out to 1,000, 1,000,000, start thinking of really big numbers. They're not even in like the same, insert the biggest thing on earth. Guys, stop talking, please. Okay, stop and check out. Questions on that? All right, so let's talk about, do I want to talk about that? No, I don't want to talk about that. So let's talk about what a logarithm is. What's our rigorous definition? Logarithms solve for exponents. And now that we've learned something in a previous chapter, we can bring it to this chapter. They are the inverse of an exponential. In other words, they solved for that exponent. They are the inverse of an exponential. So in other words, let's take a look at an example here real quick. 3 to the x power is equal to 15. 3 to the x power is equal to 15. Here's what I'd like you to do. Out to the 10th, what is x? Out to the 10th power, what is x? Give you 2 minutes for this one. And Mark gets that math.
I think these ones are good with other people, and these ones are out of 60.
15, 39, 3, niece. 15, 39, 4 times 12, 39, 51, 59. What kind of smoking? How did I get 60? 1, 2, 3, 15. Plus, these are worth 4 each. 1, 2, 3, 4, 5. 20, 35. 47, 55. I count 63 points. Can you count? We may have to go back and correct all these.
Oh my. Bars.
That gets so screwed up. Can you count the number? You count the number of points correct amount.
I was so happy. Yes. I don't understand that.
2.4.
2.5. Volunteer, how'd you go through that process? Niece, you want to take it? How'd you go through that process?
I went to the catalog and I clicked
Yeah.
the log button, which let me input two different values, and I put.
Yeah, but we're being forgiving of logs, which means we haven't met them yet. We're pretending that we haven't done that before.
Oh, well.
Because I do, at the end of the day, Niece, I do want you to understand like what logs are and why we use them and how we use them. So ignoring that we've ever learned logs in our life, how would you solve that?
You go into this catalog section in your calculator,
Okay. And
you click log.
no, we don't click a log. Somebody else. Spiker, what'd you do?
We moved 15 to the same side as 3x.
Okay, so 3x minus 15 is equal to 0. Okay, good. And then you graphed it. Good thinking. Okay, so 3 to the x power minus 15. Graph. That's good. Good idea. It crosses there, so we want to know where it's equal to 0. So we go to calculate menu, go to the zeros.
I like my method better.
If you consider cheating better.
Yeah, I do.
Okay, so that gives us 2 point, what we say 2.4, 2.5. 2.5. Okay, so using the graph, that's good strategy. 2.5, in fact, I'm not going to put equals, I'm going to put approximately, because 2.5 isn't going to give us exactly 15. Anybody else use a different way? I'm going to give you a bad way, but it's an intelligent guess and check. What's 3 to the first power?
3.
What's 3 to the second power? What's 3 to the third power? So it's somewhere between what? 2 and 3. And here's the bad news. Back in the day, when your parents took this class, they didn't have a log button. So what did they have to do? Then they had to say, okay, it's between 2 and 3. So they had to plug in 2.0, 2.1, 2.2, 2.3, 2.4. This is called interpolation. It's educated guess and check. It's not straight guess and check where you're just like plugging numbers in and see which one works. It's educated because you know it's between somewhere. They would have to do that for every single one of these problems. And just imagine if they had to go out to the thousands. So they determined it's somewhere between 2.4 and 2.5. So then they got to go 2.40, 2.41, 2.42, 2.43, okay. How long is this going to be fun for? So what did mathematicians invent? They invented a table. Well, not yet. And it is important to understand the progression they went through so you understand how logs came along. They invented a table with all the powers of a number. Well, okay, guess what number they put? Well, what unit is our number system based on?
Metric.
What number is our number system based on? It's base 10, right? So they programmed all powers of 10 into a table. Some calculators went out to the hundredths, some went out to the thousands, some went out to the millionths, programming one number, and we're going to have to make all of these work for 10. So we're going to have to come up with some formulas that make it work for 10. And later on in the chapter, we'll figure out ways to make it work for 10. then they chose another number to do. What was the second number they chose?
They chose E.
They chose E. Why? Because E is the natural growth constant. This is a really sloppy way to say it. But if you lock two bunnies in a room who really, really like each other and have unlimited amounts of food, no disease, no predators.
Are they opposite sex?
Shh. Yes, they're opposite sex. They really, really like each other. What's the rate of growth that the bunnies will experience? It gets closer to E. I have this book up here. It's called Mathematical Epidemiology. This guy, I remember an early Plinko thing, but I couldn't find it because I didn't know the guy had actually died. So I couldn't find it online, and that's actually how I figured out he passed away, is I couldn't find his Plinko thing. This class, we studied the field mice populations in southern Idaho. If you've ever been to Rexburg, Idaho, it's the home of BYU Idaho. At the time, it was home of Ricks College. Outside of there, that there was no predators for these field mice, and their population blew up. Our job was to count mice. So our prof, for one of our homework assignments, told us we had to drive down to Rexburg in teams of 4 and cover 24-hour shifts. So we had to stay awake from 4 in the morning to 6 in the morning and count the number of mice that we saw with our infrared goggles. And then we had to catch the mice and tag them so we didn't recount mice. Turns out the mice really liked each other. They had very few predators, unlimited amounts of food, and virtually no disease. What did their population growth start to become close to? It started to become close to E, which is why, if you remember from last year, it's called the natural logarithm, because it's close to the natural growth constant. Now, of course, why don't things actually grow at that? There's predators, there's disease. Two mice don't like each other, but they get stuck in a room together, and so they don't make any babies. They run out of food. Once there's too many of something, they run out of things to live on. But the second one they programmed, because it approximated so many things that happen. In fact, if you come back next period to Calc 2, we're talking about differential equations, and almost all those answers have something to do with E. Natural growth constant that just comes out of nowhere for a lot of different things. The problem with that is it didn't really help us solve 2 to the x is equal to 15. If you have a calculator with all the values of 10 and all the values of E, it really doesn't help you with that. So they invented this inverse of the exponential. So if you have some number, 2 to the x power is equal to something. In fact, I'm going to see if I can have 3 colors work real quick. Yep, there's 2. If you're a colors person, take out 3 different colors real quick. If you're a colors person, take out 3 different colors real quick.
Oh, I get it.
Okay, now in logarithms, what are we trying to solve for? Well, logarithms solve for the what? They solve for the x. Go back to rigorous definition. Logarithms solve for what?
Exponential.
They solve for the exponents. So what are we going to try to do? We're going to try to get x equals something. Well, here's the deal. They took all of these tables and programmed in. So they can, in other words, they've got all the powers of 2 written in there. We're just going to see which one works out. So what are we trying to solve for? We're trying to solve for x. What's that equal to? Well, notice the x came down from an exponent down to the standard level. In other words, it's what it's equal to, because that's what we're trying to solve for. How many times do you have to multiply 2 by itself to get 15? Well, we're trying to find that number of times we got to multiply the exponent. That's equal to log of our base 2 of what we are trying to solve it for. So notice where the things move. Purple moved to purple, brown moved to brown, Y moved, or that's orange, right? Orange moved to orange. And what is this? These 2 things go back and forth. If this is true, this is true. They are inverses of each other. The exponential is the inverse of the log is the inverse of the exponential. They are inverses of each other. This one, of course, is called exponential form. And this one over here is called log form. How is this pronounced? Log base. How is this pronounced? X is equal base 2 of y. Now, I asked you to be forgiving today because if you understand what logarithms do, the properties that are true for them, like the alpha you can do with it, is absolutely amazing. Like exponents go down to coefficients. Coefficients go up to exponents. You can separate multiplication by addition. You combine addition by multiplication. Like all your dreams come true. Like all the things that Beckman or Chmielewski like tells you kills kittens, with logarithms, they're right. They're true. All your dreams come true. Some small details. This is a subscript like H2O log base 2, H2O log base 2 of y. The only thing we are going to do with this today is go from one form to the other and back to the other. Put them in colors. That's on purpose because a lot of people, they can see where the color goes from one spot to the other. Questions on that? Already making more sense? Can logarithms be forgiven for prior sins? No. We'll see. Okay, let's take a look at an example. Example 1 and example 2. Example 1, example 2. So we've got log base 7 of k is equal to a. Convert to exponential form. Convert to exponential form. Example 2, let's go the opposite direction. 4 to the k power is equal to r. Convert to log form. Of course. Brenna, we're here to teach you. Of course I can. I've been looking for that book.
I got in trouble for reading this between the first and the second math section.
Who's your teacher?
Book, Mitchell. He said, "You can't have textbooks out there." Sir, it's not a textbook.
So this is a college elementary number theory book.
Yeah.
Joining this class?
No.
Oh, you look like you had lunch. Oh, Bobby Schimmel is that good looking boy in the Broncos shirt.
Colors are helping.
Do you miss skill quizzes yet?
No, there's help.
All for 2.
Okay.
I don't know.
All right, volunteers come up and do this one. Volunteers, Liberty, the first one, second one.
Do I do it on the board?
Spiker. No, you got to do it on the internet so people can see it and you can be internet famous. While you're doing that, I would like to, no.
I wonder if Liberty's mom
You-
would watch this.
Is she? Nope, no viewer, sorry.
Liberty's mom came and embarrassed her in the track meet all day. It was really funny because she was talking about watching your class. Yeah.
Nothing wrong with your parents getting smart.
She watches it a lot.
Yeah, she does. You'd actually be shocked how many parents, professor parents watch it and they're like, hey, you should have given a more rigorous definition of like logarithm.
Well, I have to do this with this thing, okay.
Yeah, otherwise it doesn't show up, I don't think.
Lots of people, especially in Iran, for some reason, watch my Calc2 class. Okay,
Do you say people's last names?
I try not to, but
I'm
sometimes.
pretty sure you said my first and last name all the time.
Great, Liberty, you forgot to explain. Make people smart.
Okay.
So you move this over, and then you move this down, and then you get
Did
it.
you have everybody in this class?
Okay.
See, I don't know how to explain this. You just do it.
And before you take off, Kinsey, just let me know.
Can you see this?
Or did you get totally done?
Because I color coded mine. So I'm just gonna show
All
you
right,
my notes because I color coded it. So I had the log 7 in pink, the K in purple, and the A in blue. And just based off the notes that we took like 2 minutes ago with the colors, I just put them into the order.
I did the same.
Yeah.
Yeah, you start, so you have this, and you realize that it's in exponential form, and so
100 is big.
Yes, yes. And, right there.
Oh, big.
Big.
It is big. That's actually really good.
And then yeah.
I like 1 mil too. All right, good job. Okay, last question, then I'll give you some actual time to work on homework today. How rare is that?
What is this matter?
None of us have our books.
We got books over there, brother. All right, solve that real quick. Solve that.
All right.
All you gotta do is solve it. Now, before you start putting in logarithm form, wait a minute. These tonight are just like 2 to what power is equal to 32? And what power does that happen to be?
5.
5, right. So what's x equal? 5, right. Because 2 times 2 is?
4.
Times 2 again?
8.
Times 2 again? Times 2, yeah, okay. So x is equal to 5.
Wow.
All right, yay. Let's have some fun work. Because I feel like we haven't had any for a while and there's some possible drug use going on.
Never misdirected.
Fun work, 350. It's section 4. Let's do 1 through 5, 13 through 17. Is that it? Is that all we can do? No.
Mr. Beckman, would you like to know how I remember how to convert it?
How?
I use the power triangle.
The power triangle.
What is that?
I'm listening, niece. 2 seconds, 30. 2 seconds, buddy.
I'm not asking a question. I'm waiting to put the textbook under the.
Oh,
so I don't have to
yeah.
keep looking at my desk.
Is that it? This is so boring. Oh, yes, then page 343. That's where these problems are.
Why can't we do 18?
You can if you want to.
See? Take the x to the y equals.
All right, notice I am changing. Notice I am changing. There you go. Have fun. You might even be able to get it done in class. How crazy is that?
You put it through the power triangle, am I right? So like this starts here and you put that there. Now it's here. This starts here and now it goes to the bottom here, the bottom of the log. And the z honestly just stays there.
Can I put this under the
Yeah, absolutely. Yep.